Well, hi there. We're going to have a look at inverses of circular functions, a truly gripping topic. So let's get into it and have a good time together. Circular functions are actually many to one, and therefore they have no inverses unless the domain is restricted to a situation where the function is one to one. Therefore, before the inverse function can be determined for a circular function, a principal domain is chosen within which the function is one-to-one. That is, if you're going from left to right across the page, looking at the graph, it's got to be going either uphill or downhill, but not both. Okay? Inverse sine, first cab off the rank. So we choose the principal domain for sine as being minus pi on 2 to pi on 2, so that in that realm, then you can see that the function starts off with a horizontal gradient there at one point only, at pi on 2, and goes up there and ends up level again. So it's at the highest point there where x is pi on 2, it's got 0 gradient as well, but only for 1 point, so that's okay. So that's 1 to 1. That qualifies as 1 to 1. So we know that x is from minus pi on 2 to pi on 2, and y goes from minus 1 to 1, and everything's good. So if you were to solve that algebraically, you'd say, okay, the inverse must be x equals sine y. So in other words, y is an angle. Y is an angle. It's in here now, you see. So if we would express that as saying, solving for y, we'd say y is the angle whose sine is x, where x goes from minus 1 to 1, because that's the domain of the inverse, which is the same as the range of the original function. Preferably we use the following notation. This is not a popular notation. It's very confusing because people confuse this with the reciprocal, 1 over sine, and it's not 1 over sine, it's inverse sine, but it is very confusing, wouldn't you agree? So we like to use y equals arc sine or y equals r sine x to denote the inverse function of sine x, okay? That's what you do. So yes, that's what I've just explained there. It is discouraged because we're confusing, a lot of people confuse this, meaning the inverse sine, with this, which means the reciprocal, or 1 over sine, right? Graphically, here it comes. Now, we're going to swap x and y, and then we're going to either rotate by 90 degrees anti-clockwise and then reflect in the y-axis, or reflect about the line y equals x. Now, I'm going to do the former in this particular case. And I've prepared this gripping little animation for you. So just have a look at this. There's the original graph. Now let's swap x and y. You see what happens to the x and y. Oh, they're swapped all right. Now I'm going to rotate it by 90 degrees. Watch, anti-clockwise. Pretty peachy keen, hey. Now I'm going to reflect the whole thing in the y-axis. Look. Yes, here we go. There it goes. And there she be. That's what the inverse looks like. That's inverse sine, okay, over that principal domain. And you can see that we've swapped x and y. You see, this is basically on the horizontal axis now, which was on the vertical axis in the original function, and so on and so on. So yes, it's truly beautiful. We've got y's inverse sine x, or arc sine x, or r sine x, the latter two being preferred. X goes from minus 1 to 1 inclusive, and y goes from minus pi on 2 to pi on 2 inclusive, and last but not least, y is the angle whose sine is x. Yes, I know that takes a bit of getting your head around, but that's what it is. Y is now the angle. Okay? Now, this is a very interesting screen here. This is Dr. Wolfman's recipe on how to sketch an inverse function as a reflection about the line y equals x, and it's very detailed, and if you follow it you won't go wrong. Draw the axes with the same scale. Here they are, and I've used the same scale. It just gets a little bit less confusing when you're trying to be reflecting things in the line y equals x and they don't quite look the same and all that kind of stuff, you know. The axes scales, if they're the same, it just makes everything a little bit more, lines up properly with your brain and your spatial awareness. So then you draw the line y equals x, there it is, and then what you do is you draw the original function. In this case we're going to do y equals sine x. Now, there it is, and it just touches, the the line y equals x, the function does, at the origin. It starts off with a gradient of 1, like the line y equals x, but then it kind of deviates away. So that was very hard to actually get that degree of definition on this graph, but that's what it does, right? So then you mark in all the relevant asymptotes and points, such as end points and axes, intercepts, and intersection points with the line y equals x. So I'll do that now. Yeah, that's the end points for the principal domain. That makes sense, doesn't it? That makes sense, doesn't it? There's no asymptotes, and that's the point where the only point where that graph intersects with the line y equals x is the origin, actually. Then you swap x and y with all of the above points, ensuring that they are the same distance on the reflected side of the line y equals x as the originals, taken at right angles to y equals x. Now that was a big mouthful. I'll show you visually. Watch this. Yes, see what you do, it's you basically draw a line from, say, this end point here. It's a known point. You draw a line perpendicular to the line y equals x, and whatever that distance is that you have travelled to get to the line y equals x, you travel exactly the same distance, still at right angles, over the other side of the line, until you get to that total distance has elapsed, the same distance that this point was on this side of the line y equals x, and you swap x and y. Isn't that amazing? And you'll get the reflected point, right? And it's the same thing down here. So now we've got really something to chew on now. That's how you do it, guys. We'll draw the reflected graph in stages, not getting too stressed about it, between known points as the mirror image about the line y equals x, treating the line y equals x as a mirror. See, there's the first bit I did, and the second bit's coming up, and there it is. It's just great. Yes? And this one here, this graph here, whilst these were horizontal, the gradient of this endpoint here is it's flat. In other words, it's level. This one here is going to be vertical. That's what inverses do. This one here is going to be vertical as well. So if you're drawing inverse sine x, for heaven's sake, make that vertical at that point and at this point here, right? Yes, it makes sense. If you think about the gradient as dy dx, right? Something y over something x, well, if that's naught over 1, if you like, as level, well, this is going to be 1 over naught, which is undefined. That's why it's vertical. Do you see? Hopefully you do. Now, NB, yes. The gradient of the y equals sine x graph is 0 at the end point, so I wanted to point that out. And the gradient of the inverse is undefined at the end point, vertical. Please get that right, and when you're drawing those things, and don't do something that's kind of like, looks a bit sloppy and isn't right. Right, let's go. Inverse cos and then inverse tan, and then we'll do some examples, I think. Inverse cos. Now, what they do for inverse cos, the principal domain for cos, they choose as 0 to pi. 0 to pi, because you can't choose the same principal domain as you did for sine, because if you just do a little visual in your head of cos from minus pi on 2 to pi on 2, you will visualise a hill going up one side and down the other. You will. And that's no good, because you have to have it 1 to 1. So, and that makes sense because cos is actually the same as the sine graph, except it's out of phase by 90 degrees. So we have to choose a different domain, so they chose 0 to pi. There it goes, see? And it is, you see it's going downhill, completely downhill. So this is the original function y equals cos x. The principal domain is from x goes from 0 to pi, and y will go from minus 1 to 1 inclusive, and that's inclusive as well, that 0 to pi. Right, let's go. So for the inverse, the same procedure as we did before algebraically. We'd say the inverse is x equals cos y, where y is now the angle. So in other words, we can write that as y is the angle whose cos is x, where x now goes from minus 1 to 1 inclusive, which is the domain, which was the same. This is the same as the range of the original cos function with the principal domain. Yes, good. Preferably referred to, again, as arc cos or r cos, right? That notation is very confusing, so please give it a miss, because it's confused with the reciprocal, this beast and this beast. How confusing is it? I mean, why did someone ever start using that notation? I don't know. So graphically, now we're going to swap x and y, and yes, you either rotate 90 degrees anti-clockwise and then reflect in the y-axis, or you reflect about the line y equals x. Now in this case I'm going to do the latter to show you that approach. There's our original function, so what we've got to do is do a line y equals x, and then we've basically got to, I'm jumping the gun. We've got to do the reflection about that. So I suggest you do that in 2 stages. Why not do this bit from here to the green line as one bit for reflection, and then do this bit on the other side as the other bit for the reflection, and then making sure that they basically line up with the same gradient, smooth curve here at where the 2 stages that you've drawn actually meet up. So I'll show you what I mean. Here's the first bit, right? There's the first bit. Does it make sense? And see how you've swapped x and y? That was y there, and now it's x here. Now we'll do the second bit. There she be, right? It's beautiful, isn't it? Truly beautiful. So that's the summary. Y equals inverse cos x, or arc cos preferred, or r cos preferred, meaning inverse cos. X goes from -1 to 1 inclusive, and y goes from 0 to pi inclusive, and y is the angle whose cos is x, yes? Alright everybody, you okay? Good. Well, now we better do, oh, there's a nice box for us. Now we better do inverse tan now, inverse tan the man, and he's different. Of course, he's a different beast altogether, because tan has asymptotes and sine and cos don't. So we choose the same principal domain as sine, with the exception that the end points are not included, right? From -π2 to π2, but this is round bracket, right? Round bracket, because at those particular spots, tan is not defined. No, it's not. So, yeah, you can see, can't you, right? See, these are the asymptotes here at -π2 and π2. So y equals tan x. X goes from -π2 to π2 non-inclusive, and y is anything, basically, from -infinity to +infinity. That's the original graph of tan with the principal domain. So for the inverse function, let's do the same thing as we've just done for the previous 2 functions algebraically. The inverse would be x equals tan y, where y is now an angle, right? Y is now an angle. So therefore, solving for y, we can say that y is inverse tan of x, where x is any real number. Again, yes, I'll just explain here, that's the domain, which is the same as the range of the original function. Okay? So it's also preferably referred to as arctan or artan. Yes, the same thing for sine and cos. Yes, that's very confusing, and we avoid the notation because people confuse it with reciprocals. Now, graphically, again, you can swap x and y, and then do the old flipperoonie around the y-axis, I mean, or you can reflect about the line y equals x. Now, in this case, I've reflected about the line y equals x because it's less trouble for me to do than those animations, which are pretty tricky and time-consuming to organise, so I hope you don't mind. So, there's the line y equals x. Tan's a little bit in the same realm as sine was, because the gradient of tan starts off at 1, but instead of going down, it goes up, right? So really the only point of coincidence with the line y equals x is the actual origin itself, okay? But that's pretty hard to represent with enough definition on a curve like this. But you get the message, don't you? Now, yes, I've drawn those asymptotes in. So, you know, what do you think is going to happen to those asymptotes, guys? This one is going to become a y asymptote equals -π2 for the inverse. This one's going to become a y asymptote of y equals x equals y equals pi on 2, because you swap x and y, don't you? Yeah. So there they go. There they are. Now we've just got to basically do the reflection of this black graph about the mirror of the green line. Now, I would think you would do that in 2 stages. If I was doing it, I'd go from here, right, like that, and I'd go from here, like that. Yeah, and make sure they join up with a smooth curve in the middle. There's that one, and there's that one. Yes, very good. But that's it. That's what it looks like, right? And there's the whole picture, all drawn in, and, you know, with swapping x and y all over the place, yes? That's right. So, with the black graph, usually the point of reference that you use for tan, the original tan graph, is pi on 4, going to 1 on the y-axis. Well, with the inverse, it's the reverse. Okay, you've got 1 on the x-axis going to pi on 4 on the y-axis. That's what all that stuff's trying to represent. And down here we've summarised it. Y is the inverse tan x, preferred notation arctan or artan. X is any real number, and y goes from minus pi on 2 to pi on 2 non-inclusive. Okay? Right, let's get going. Well, of course, wouldn't you know it, we've got to do the old transformation throughout the nation trick, because that's what makes these things hard. But look, it won't be hard for us. I'll show you what to do, and you'll find it just easy peasy if you just follow the rules. So A, we've got y is inverse sine 2 minus 3x. Well, what a mess. Don't worry about it. Look, you just follow these rules, and Wolfman will show you. We're going to consider the base model. Y equals inverse sine x as the original function, and then what would you have to do to the original function to get this beast here? And then it'll help us. If we know what the transformation steps are, then it's very easy to then derive the transformed function. So that's going to be the transformed function. Now, what I do in the way I do these transformations, if you're not sure about transformations, PS, go and look at my methods videos, chapter 3, MM3, B, C, D, E, F on transformations, and you'll see how I do them. They're very, very straightforward if you just follow the rules, okay? Now, that's the transformed function. They're in equivalent for what I call equivalent form, where all these extra terms, in this case there's a 2 and there's a 3, compared to this, they're actually belonging to an x or y term, so that they're actually directly affecting the x or the y term, in this case the x term, and we can then rattle off what the actual effects of them being there are very easily, because what we then do is we equate equivalent terms and we say, okay, well, this y is equivalent to this y dashed. There's no transformation happening in the y, but there definitely is in the x. Okay, so we're saying that this 2 minus 3x dash is equivalent to that x. Now, what we're doing here is, this is my terminology, we're doing a backwards transformation, which I mean to say we're given the original base model and we're given the final product, okay, and I want to go backwards to work out what were the steps that I took to get from here to here. That's why I call it backwards. And for backwards, we solve for y dashed and x dashed. These two equations, I've got a name for everything. These two equations, I call them the key to everything, because they really, really and truly are in terms of transformations. They are the key which unlocks the door of transformation. So, without any further ado, we can say that y dashed equals y. That's already got y dash the subject. Then making x dash the subject of the second one, we would get that. Okay, now, the y values are unchanged, but regarding the x values, we've got that. Getting rid of that bracket, which makes things a lot easier. So you can see, in order to get x dash, the transformed version of x, from the original version of x, you've basically got to do minus 1/3 of the original value of x and then add 2/3. So, to get from x to x dash, we have a dilation of a factor of 1/3 from the y-axis. That's this. X is becoming 1/3 of its original value. That's how you say it in mathematical lingo. Okay, and then I'm going to these are logically read off. They're logically read off. Okay, you read them as you see them, right? This is the logical way, as opposed to another way which is often taught, which is you've got to think in reverse all the time. I prefer this method. Dilation factor of 1/3 from the y-axis. Now, if x is becoming reflected, x is going to minus x. That means we've got a reflection in the y-axis, and then we've got a translation of 2/3 in the positive direction of the x-axis, or to the right. That's what we're doing, and that's all there is, because there are no y transformations. Now, the easiest, so that, in other words, the height is going to be kept the same. The y is going to be kept the same. All of the stuff in the vertical plane will be the same, but we're fiddling with the x stuff, yes? The horizontal dimension of this thing. Now, the best way for you to do it, guys, you can see that this thing's been reflected, so it's been flipped around 180 degrees on itself, right? Squashed into 1/3 of its value and then pushed over by 2/3, the poor thing. It's a wonder it doesn't have to go to hospital. So now let's just do the end points and see what happens to them. That's the best way to really get around this. So x originally, in the original function, went from -1 to 1, didn't it? So when x is -1, x dashed, according to our key to everything, will do that, which turns it into that, right? What about when x was +1? Well, according to the key to everything, that's what happens there. Yes, this is the formula here we're using. That's the key to everything. Now that goes to that, and that'll go to that. Now that's fascinating. Look, you see how that's gone from -1 to +1. That's the low value. From -1 went to +1. The high value, 1, went backwards to a third. That's what I'm saying about it being reflected. You know, it's been swiveled around on itself, so it's, 180 degrees swivel around about the y-axis, if you like. That's another way of thinking of it. So let's just try and see if we can flesh that out in a minute. But that's what I'm saying. That point there goes to that point there. That point there goes to that point there. All right? Now, if we do it graphically or visually, it's so much easier. So let's say that's our original graph, right? Now, this point here, where's that going to go? That's going to go to +1, isn't it? So let's just represent that. Boom, 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 boom. There it is, yes. Now, what about this point here? That goes backwards to a third. So it's going to go boom, 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 like that. Now you can see, as I said to you, the height just does, height is preserved. So the height is the same as before. So this is going to go like that. Oh, I'm a bit off balance there, but the midpoint, that if that's 1/3 and that's 1, the midpoint here is going to be 2/3, right? So it'll go like that, and that's what the curve will look like. Yes, it's easy if you do it that way, right? Look. It's better to be sure. When you get really good at them, you'll be able to go faster. But while you're learning this stuff, it's better to go slow, because slow and steady ultimately wins the race. You know, you want to be the tortoise rather than the hare, because eventually you'll become a hare. But you have to be a tortoise first. Righty-ho. This is the tan one now. Right, so we're going to do the base model as the original function. Yes, the base model is the original function. Then we'll work out what to do, what are the steps are to get to there, and then we'll be a lot better off, a lot clearer in what we're doing. If you were doing what's called the Dr. T technique, you would just read that straight off, and you'd say, okay, that's a translation of 2 units to the right, and it's also a translation of pi/2 upwards. That's pretty fast, but that's a learned technique. It doesn't have a lot of logic behind it, and I'd prefer to use the logical technique, So what I'm going to do is the logical technique, so you really learn what you're doing and understand it properly. So y dash transformed y is equal to inverse tan of x dash minus 2 transformed x plus pi/2. Put them in equivalent form. This pi/2 is no good. He's not belonging to an x dash or a y dash. He's out there on his own trying to be independent, and he's not allowed to. He's got to affect directly the x dash or the y dash. And when I say he's got to belong to the x dash or y dash, what I mean is he's got to be added to or subtracted from x dash or y dash, or he's got to be multiplied by x dash or y dash, or he's got to be divided into x dash or y dash. That's what I mean. So that's the best. This is the best way to do it. Now he belongs to the y dash, and they're in equivalent form. So now we can start equating equivalent terms. Y dash minus pi/2 equals y, and that's x dash minus 2 equals x. So there's a translation in both x and y, right? There is a translation in both. So y dash is y plus pi/2. We make y dash and x dash the subject when we're doing a backwards analysis, and we can now read it off as I was just saying before. Right, so then to get from x and y to x dash and y respectively, you can see that you've got a translation of 2 units to the right and a translation of pi/2 up. Yes, that's true. Now, we've got to see what we can do with that, okay? Now, for the graph of y equals inverse tan of x, we know that x is all real numbers, don't we? And we also know that y goes from minus pi/2 to pi/2 non-inclusive. So we've got to basically work in a translation of 2 units to the right and pi/2 units up into all that to figure out what the new graph's going to look like. And it isn't that hard, really. Alright, so what am I saying there? Yes, therefore for y dashed, yes, looking at the x part of it, If you translate that over by 2 units to the right, you'll still be all real numbers because you're already dealing with all real numbers in the first place for the x, right? So that really hasn't changed anything, but it has shifted the graph 2 units to the right. And in that context, we probably look at it's better to look at the central point, if you like, in terms of x for that graph, which would be where it normally would have hit the y axis, right? And then work out what happens to that point. It's actually a point of inflection, but I won't confuse you with fancy terms yet. So with the y, when originally y was minus pi on 2, we've got to add. Remember, we're doing a translation of pi on 2 up, so you've got to add pi on 2 and you will get y dashed would now be 0, okay? And when y was pi on 2, y dash will now be adding another pi on 2 to that to get pi. So that's what's going to happen. The original range was from minus pi on 2 to pi on 2 non-inclusive. The new range will go from 0 to pi non-inclusive, okay? That's pretty simple. Now, yes, this is the thing I was just alluding to before. This is kind of like the central point where the original graph of y is inverse tan would go through 0 and 0. Okay, so that point, why don't we reflect that point 2 units to the right and pi on 2 units up to get a bit of a perspective on what's going on. This can be a bit hairy when you're doing graphs that are defined for all of real numbers, which they are. This is in the x realm. So that will transform to the point, yes, 2 and pi on 2. So the y-intercept, we better work that out because this thing does have a y-intercept. So originally it used to be just here for the original function, but for this we've got to plug it into this crazy equation here. So when x is 0, y will now be inverse tan of negative 2 plus pi on 2, whatever that is, whatever that is on a good day. But here's the new graph. Look, you see that's that central point that used to be on the origin for y equals inverse tan x without any translations. That's been moved to the right by 2 and up by pi on 2. And our new y-intercept is this, right? That's our new y-intercept. Where x is 0, y will be that. Is that okay? Now you'll notice here these asymptotes are y equals 0 and y equals pi, so the whole thing has been shifted up by pi on 2. I think we've pretty well nailed that now, haven't we? Yeah, we have, okay. Goodbye, Mr. Graph. We did you, and we did you faithfully. Now what's this stuff? Oh yes, this is riddle time. Riddle time, particularly with part B, it's riddle time. Part A isn't such a riddle, but you've got to understand what you're reading when you see this stuff. Now, we're looking at, let me say it in English because that's really what you've got to do when you're dealing with this mind-bending inverse stuff. That's saying the angle whose cos is minus root 3 on 2. And look, I recommend that you do that every time until you get this firmly ensconced in your brain. The angle whose cos is minus root 3 on 2. Oh, I sound like a nagger, don't I? Don't worry, I'm only looking out for your welfare. So this means, yes, the angle whose cos is minus root 3 on 2. Okay, now if you look at the graph of cos with the principal domain, you've got to work out which angle is it that has a cos of minus root 3 on 2. Well, we're going in, that's quadrant 1 from there to there, from 0 to 90 or 0 to pi on 2. This is quadrant 2 from pi on 2 to pi. So, okay, think about cos. Well, this is where it's negative in here, in quadrant 2, right? That's what we're dealing with, a quadrant 2 angle, okay? Yes, that's where sine is positive, but cos is negative. Now you've got to think, okay, quadrant 2 angle required. Now, if we were in quadrant 1, what angle would have a cos of root 3 on 2? And I hope you know this. It's pi on 6, right? So we're dealing with the equivalent of a pi on 6 angle, but in quadrant 2, which would be 5 pi on 6. 5 pi on 6, right? That is the answer. Now you can do that. I know you can do that, okay? Good, so we can put a line under that and finish it. Forget it. Here comes B. Now this is riddle time. B1. Right, we're dealing with that thing. Now look, let me just work this out with you. The answer to this, before I get all hung up in it, is pi on 3. Yeah, that's the answer, is pi on 3. Now why, oh why, oh why is it pi on 3? Well, you think about this. Look, we're asking for the angle whose sine, is sine pi on 3. The angle whose sine is the sine of pi on 3. Well, you're just talking about pi on 3, because pi on 3 is the angle which has a sine of sine pi on 3, isn't it? Do you see what I'm saying? This stuff is a little bit like taking the square root of something squared. Like this kind of thing kind of undoes the effect of this. So, yes, so the answer is basically, yes, so basically the angle is pi on 3. All right? Do you see? You think about it, you know, it's like a mind buster, this stuff, a brain buster. So that's the answer. Now, similarly, this one, this is just where I've got the cos bit here and the inverse cos bit in there. So if I said that again, I want the cos of the angle whose cos is root 3 on 2. I'll say it again. I want the cos and the angle of the cos of the angle whose cos is root 3 on 2. So I'm looking at the cos. That is the cos. That is the angle whose cos is root 3 on 2. I want the cos of it. Well, it's root 3 on 2, isn't it? Do you get it? Of course you do. It's root 3 on 2. So just remember, if you have this gobbledygook here where you're just kind of undoing the effect, one undoes the effect of the other, you just deal, the answer is whatever's in the bracket here, right? That's basically it. Okay, riddle time's fun, isn't it? Now, this one's not so, this is not basically quite so straightforward, but it is actually very straightforward when you just look at it. Now, because we've got cos here and inverse sine there, so you've got to think what you're doing. You just you boil it down into two simple steps. You peel the onion bit by bit from the inside out. That's what you do. So what you've got to look at is first of all, I want the angle whose sine is a half, right? With the principal domain that we were dealing with for inverse sine or just sine, which angle has a sine of a half over that principal domain of sine? Well, first of all, in quadrant 1, okay, in quadrant 1, we're dealing with positives. In quadrant, this is basically quadrant 4, this thing, isn't it? That part. Yeah, so we're dealing with positive a half, so we must be dealing with an angle in this quadrant, right? Now, what is the angle in quadrant 1 that has a sine of a half? Yes, it's pi on 6, right? So therefore, now we can basically get down to where the rubber hits the road and replace what's in that bracket with pi on 6, right? So we want cos of pi on 6, which happens to be root 3 on 2. Yes, that's the answer. You see? Riddle time. We won again, yes? Now this last one is very similar. This is the angle, whoops-a-daisy, what am I saying? The angle whose sine is the cos of pi on 3. So we peel the onion from the inside out, if that was possible, but that's what we're doing in maths. So let's work out the cos of pi on 3, then work out what angle has a sine of that value. Now come on, what's cos of pi on 3? Yes, did I hear you say a half? Hope you did. That's right, a half. So now we can take that half and put it in here. Okay, so we want the angle whose sine is a half. Okay, and the angle whose sine is a half, you know the answer to that, it's pi on 6. Yes, 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 that's it, right? Wasn't riddle time fun? So, okay, now, what's this stuff? Find the implied domain and range. Oh, yeah, okay. That's all right. We can do that. That's transformation stuff again, really. So let's do the first one. So we're going to we'll start with our base model. Yes, y equals inverse sine of x. That's the original function, and we're going to work out what did we have to do to get to there. So that's, I call that working backwards to get the steps. Once you've got the original and the final, which is this. And we work out the steps. Once we work out the steps, we get the key to everything, and then we can work out easily what's going on by using the endpoints of the original and transform them, okay? Right, that's the transformed function. I'm putting dashes here just so I don't get confused with what I'm doing. Now, they are in equivalent form. They are. So we can just do a straight equating of equivalent terms. So we can say that y dashed equals y, and 3x dashed minus 1 is equivalent to x. In other words, this here is equivalent to that. Now, with backwards, as I call it, backwards transformation, you make y dash and x dash the subject, so that means we make x dash the subject and we get that. Yeah, that looks right. Okay, so that is our recipe for success. That's the key to everything, guys. So, hence the y values don't change, but the x values certainly do. So, let's go with that. Here's our original extreme points, at either end of the domain. So let's take each of those in turn. When x was minus 1, what would the key to everything tell us that x dash becomes? It becomes a third. When x, oh no, it doesn't become a third, it becomes 0. That's right, I just got ahead of myself. That's right, minus a third plus a third equals 0. Yes? It's been hot today, my brain's a bit cooked. So when x is 1 plus 1, when x was 1, x dashed would be, according to the key to everything, looks like 2/3, doesn't it? Yes. Now that's pretty interesting, isn't it? Yes, it's one of those flipperoonie ones. You see, oh no, it's not. It's not a flipperoonie. No. This one here, when x was minus 1, that goes to 0. When x was plus 1, that goes to 2/3. No, they're still in the same relative order, because 0 is less than 2/3, minus 1 is less than plus 1. It's this one up here. It's number B that's a flipperoonie because of this minus in front of the x here. I was just getting a bit confused. So, okay, so what are we saying here? So, minus 1 to 1 domain inclusive transforms to 0 to 2/3 domain inclusive. So now we have the implied domain, and we're laughing. So the implied domain is from 0 to 2/3 inclusive, and the range is unchanged from minus pi on 2 to pi on 2, okay? Now, you're still with me. This is a long session. This is a heavy session, this one, so let's just keep going and get through all this. The next one, right? So the next one is this. So, yes, that's as for A, let y equal the base model, y equals inverse cos x, and therefore our in equivalent form, I've speeded up the process by just writing that straight in equivalent form, that's this one. So we equate like terms, and we get this thing here, this thing here. Yeah, that one becomes that, and x, solving for x dash, we get that. Now that's our rule, that's our key to everything, so let's just go with that. So for y was originally going from 0 to pi, that means y dashed will be double. It's double. See, the key to everything tells us that. So it's going from 0 to 2 pi. Now, it's regarding x. X originally went from minus 1 to 1 inclusive. Now it's going to go according to, yes, the key to everything. Let's work it out. That goes from minus 1 to 4 over 3. And from plus 1 it goes to 2 over 3, which, as I thought, the relative... that's going from a low to a high, and that turns it into from a high to a low. So it's been flipped around by 180 degrees, and that's what this minus sign up here does, right? So that domain transforms to that domain. So we've got it now. So we're just referring to these in the proper order of domains. 4 over 3 to 2 over 3. You really should write that as 2 over 3 to 4 over 3, shouldn't you? As a proper interval. The lower number first. So that's right. So therefore the domain is from 2/3 to 4/3 inclusive, and the range is from 0 to 2 pi inclusive. And let's hurry up because I've been too long explaining all this. Now this here, we're finishing with a bang, guys. This is a horror. This is well, this is actually a composite function, and a lot of people think they're absolutely dreadful things, but we'll prevail. Don't you worry. Y is sine of minus inverse cos of x. Find the implied domain and range of that, where sine has the restricted domain of what we would expect, the principal domain of from minus pi on 2 to pi on 2 inclusive. Now, you can bet your bottom dollar, ladies and gentlemen, there's going to be problems when you've got a fog and goff. I call them fog and goff. Composite functions, f of g or g of x. Now, let's just draw a diagram so we don't lose our cool. This is a composite function. So in the first stage of the process, we've got this one here. The one in the bracket is the very first one. That's inverse cos of x, and then that's the second stage of the process is sine, right? That's what, and what we come out the other end is basically sine of minus inverse cos of x. Now, let's work out the compatibility issues in the middle here, because I'll guarantee you there will be some, and that causes us to do some surgery. Now that's negative inverse cos. Normally inverse cos would be up here above the x-axis, but the negative flips it all upside down. So, or I say its domain would normally be from -1 to 1. Its range would normally be from, well, you'd have to say minus pi to 0. Yes, now let's look at sine now. Sine, on the other hand, it's comfortable with minus pi on 2 up to pi on 2, and its range is from -1 to 1. So look, alarm bells, alarm bells, alarm bells. This is no good. We've got compatibility problems here. As you can see from the above, the range of this little gremlin coming out here, what the y values, if you like, that spit out here, are outside the ambit of what this thing can cope with. So that's no good. So we've got a problem. We've got a problem. We must make sure that the range of this is wholly contained within the domain of sine x. So we better just get a number line to the rescue and have a look. So that's basically, now, okay, so a simple number line. I'm showing you that the range of inverse or minus inverse cos, wait a minute, I'll just fix that up. Yeah, the range of inverse cos, I've just fixed it, of negative inverse cos. I just didn't have a negative sign in there, so pardon me, I've fixed it up now. That goes from minus pi to 0 inclusive, but the domain of sine x is basically minus pi on 2 to pi on 2. Now you can see that part of this bit, this lower half of this is no good for this. It's not wholly contained within. And what's on the top line here of the number line must be wholly contained within there, or completely coincidental with. Otherwise, we've got a problem, a major problem. So this is the bit that we have to choose. That bit where the two lines are coinciding. Okay. So we've really got to reduce this output here. That can't be from minus pi to infinity. It's got to be from basically from minus pi, not to infinity, what did I say? It can't be from minus pi to 0, it's got to be from minus pi on 2 to 0, okay? So we're chopping off half of it, that's what I'm saying. So yeah, so we restrict the range of minus inverse cos to minus pi on 2 to 0. Now have a look at the graph and I'll show you a little Wolfman illustration, right? That's the bit we want, that's the bit, that's the range we want, right? And so therefore we'll have to restrict the domain of it at this side here accordingly, so that it only produces this green part of the curve and this part here, this highlighted part here of the range, right? So this means that the range of minus inverse cos of x will be then wholly contained within the domain of sine of x as required. So this in turn means that the domain of inverse cos of x, negative inverse cos of x, needs to be restricted to 0 to 1. That's the domain to produce the range that we require in this critical central region here. Now have a look at the graph again, and I'll show you the illustration, the Wolfman illustration of the domain that we need in this graph to produce this green part of the graph. There, vertical lines from the y bits down to the x-axis shows you the part that we want for the domain, which is that bit, which is basically 0 to 1, right? Do you see that? Yes, that's what you do. Hence the domain of the composite function that we require, which is what we're asking, what they're asking is for up here, the implied domain, will be the domain of this, which is basically, or part of the domain of that, which goes from 0 to 1, right? That's the domain of the composite function, is the partial domain, if you like, of minus inverse cos x, which is 0 to 1, and that gives us a range required coming out the other end, which is going to be what's produced in this graph as the range. Now, if you have a look, it's going to be from minus 1 to 0. So that's going to be the range coming out of this function here, and hence the range of the whole composite function is going to be that. Now, you look at the graph and I'll show you, right? Look at this graph here. You ready? There. That's basically, now, what am I saying there? I'm saying that the domain I'm putting into it, is basically from minus pi on 2 to naught, right? Minus pi on 2 to naught, which was the range of this thing there. That range there is the domain from minus pi on 2 to naught going into this one, and therefore that will produce a range of from there, see? From minus 1 to naught. Do you get that? Right? That's it. That's how you do these composite function horrors, right? And that's the answer. That is the answer, and that's the end of our video. My goodness, what a horrendously long video. I'm getting out of here. Go and have a nice cup of tea, have a rest, and mull over that and do plenty of practice, and we'll see you next time. Bye-bye.